Hello and welcome to this lecture. My name is Chibuzor Marcel, and I'm the founder and the director of the Pan-African Citizen Science e-Laboratory. So today we are going to be learning about the total solar eclipse that is going to happen on Wednesday next week, August 12th. Okay, we're going to learn some science and some activities around it. So I want you to pay attention. So as part of the table of content of my lecture, I'm going to be introducing solar eclipse, and also I'm going to be explaining why solar eclipse has always fascinated humanity from ages. Then I'll talk about the historical significance of solar eclipses, and then I'll give an overview of the August 12th, 2026 total solar eclipse. I also talk about the science behind solar eclipse, that is the understanding the sun, earth, moon system. Then I also answer the question can the moon why can the moon completely cover the sun? I talk about types of solar eclipses and why total solar eclipses are rare at any one location. Then I'll conclude my lecture with giving some safe guidelines on how to observe solar eclipses. So, this lecture is sponsored by the Free Astro Science Group. So, introduction. What is solar eclipse? What is solar eclipse? You can see it from the picture. So, what do you think is happening here? What they say, so you can say that a solar eclipse is an astronomical event that occurs when the moon passes between the sun and Earth and then casting its shadow on Earth. When the moon passes between the sun and Earth. So as you're looking at this video, this animation, you can see the sun there, and we here are on planet Earth, and then the moon is passing between the sun and us, on the moon. Us on Earth. So what happens is that as it passes between the two bodies, the moon casts its shadow on Earth. So that location, the point on Earth where the shadow falls at, experiences the solar eclipse, while the rest of the Earth remains like as nothing is happening. Okay, right now this is afternoon period. Eclipse could be happening here, but if you are in East or in America, you might not even experience that. So it's a local event because it has to do with the shadow of the moon casting on Earth, and it's just a little, you know, little shadow, not the entire moon. So that is why it is important to always emphasize on the shadow. Because if I talk about the meaning of solar eclipse without including this shadow factor, you may go out with a very wrong perception or perspective about the solar eclipse. So it is actually a shadow thing, a shadow thing. So I'm going to emphasize on that in the preceding slides. So in other words, from what I've just explained, to have a solar eclipse, you're gonna need three ingredients. You're gonna need the sun, you're gonna need Earth, you're gonna need the moon and its shadow. You need the moon and its shadow. Okay, so now why solar eclipse? Why has it fascinated humanity for centuries? Okay, why has it fascinated humanity for centuries? Just imagine, like this is afternoon period. All of a sudden, everywhere becomes dark. How are you going to feel about that? Like, has that kind of thing happened to you before? Normally we are used to experiencing power, power outage, electricity, or at least electricity is provided by the government. So maybe there's something that happened to the power grid and there was a national problem, and that is understandable. Okay, since we were born, we have always seen the sun there. Okay, we have always seen, it's almost like static. Nothing has changed the fact that the sun is gonna rise every morning and set in the evening. Okay, and all of a sudden, the sun just disappears. That is actually very troubling to me. So I understand the feeling of ancient people when such kind of thing happen. I know they do not have modern science. Okay, so it fascinated them and it also caused a lot of fear. So you can see this picture here. These are the people observing the solar eclipse. Okay, so it happens. It usually happens in the daytime. Okay, it usually happens in the daytime. Okay, so just all of a sudden the area becomes pitch dark. You know, the temperature the temperature reduces considerably. Okay, everywhere maybe you are if you're in a hot climate, maybe Saudi Arabia or all these Arabian countries, we had temperature is usually very high. All of a sudden, maybe when the eclipse happens, everywhere just calms down, and maybe you begin to see stars. Oh my God, this looks like the end of the world to me. Honestly, it looks like the end of the world. So you start seeing the everywhere just becomes like dark. And if you check your time, maybe you just came to the office by 8, and maybe the thing happened in the afternoon by 12. You begin to wonder, no, this is wrong. So you might even be afraid of your life. And they begin to see birds, because birds are shocked, the animals are shocked, because all of these things have been incorporated in our body. So we have not experienced this before. So the birds may stop singing and return to their nest because they have probably thought that, okay, it's nighttime, time to go home. Then you have these nocturnal animals, those animals that are usually very active at night. They just start coming out because they thought that night has come. And the suns, you're going to see the sun atmosphere, and you're going to see the sun, we call it the corona. You're going to see the sun atmosphere. Okay, it becomes very visible. Okay, so, and the landscape, the entire environment changes, becomes unusual. So that is why it has fascinated humanity. Okay, but however, unlike other astronomical events like meteor showers or even lunar eclipse, okay, solar eclipse do not need equipment to notice it. It's not like you're at your office and something happens on the heavens and you're hearing it on the news. When solar eclipse happens, everybody is gonna know. Okay, it affects everything, and you don't need any telescope. You don't need any equipment to to notice it, to observe it. Although if you want to get detailed part, you want to see it in detail, you can use equipment, but you can just be in your office, all of a sudden there is darkness. So you don't need any equipment to tell you that. So because of this accessibility, okay, but luckily it is not the end of the world. It is not because of the end of the world. Luckily for everybody, okay, just luckily. So it is just something that is natural, that is just going to happen within a few minutes, and everything is back to normal. Okay, so because of this accessibility, that is what makes it a very important tool for outreach. So during that period, okay, we can predict it anyway. During that period, teachers bring their kids outside to teach them about eclipse. Probably they have been teaching them about eclipse in the class, so they have not experienced it before. They only hear it on the news. So during that time, teachers bring their students outside to educate them about eclipse and give them these classes to view eclipses. So it's an important and powerful educational period. Okay, and also beyond their visual beauty. Okay, solar eclipses also remind us of the remarkable precision and the predictability of celestial mechanics. Okay, now with our modern science, we can predict when they are going to happen. It's not something that is just going to happen. It's not a spiritual thing. Okay, we can predict it because we have classical mechanics. Okay, we have these equations that helps us to calculate motions of objects. If you have their acceleration, you can predict where they will be at a particular time. So you can always use those equations to predict them. You can predict, like we told you, August 12th. It is not a guesswork. Okay, it is like 100% certain it's going to happen on August 12th. So this is the beauty of modern science. Okay, so we can predict it even in the next 100 years, even in I don't know if it is actually significant to even talk about it, but there are some applications. There are some applications you can go forward in time, can go forward in time to check how, you know, if there's going to be an eclipse. Okay, for instance, you can even go back in time. You can go back in time. Maybe in the history books, you read that an eclipse happened in this place and it was recorded by historians. You can decide to go to your stellarium and go back in time at that location to know if you can verify the story, because we have incorporated this mechanical, these physics equations those in those applications to go back in time. So it helps us to even predict it, uh, to predict when it's going to happen. So let us look into the historical significance of the solar eclipse. Long before our modern scientific advancement, okay, solar eclipses were mysterious, of course, and often frightening events. Many civilizations interpreted the sudden darkening of the sun as a supernatural occurrence. Okay, some, like for instance, the ancient Chinese, they thought it was a dragon. Okay, so during the eclipse, the dragon is about to swallow the sun, and they get frightened. So they think, okay, so what made sense to them was to start beating the drums. So they start beating the drums. So as they beat the drum, they beat it loud enough so that they would chase the dragon away. So that was what they thought was happening during solar eclipse, total solar eclipse. How about um, how about the ancient Indians? The same story, but this time they thought it was a god, a demon god called Rahu. Because during the time it swallows the sun and vomits it again. So that is the kind of explanation they came up with for eclipse. And then we have the Vikings. The Vikings thought that a wolf is always chasing after the sun. It's always chasing out of the sun. So during the time of the eclipse, that is the time it captures the sun. Okay, it swallows it and vomits it again and continues chasing it. So, and even in some African traditions, they see it as a divine occurrence. It's a divine phenomenon. So they see it as a sign of reconciliation and peace. Okay, they see it as a sign of peacemaking. No, these are just few I could just create. You can explore others. In some cultures, it is not a good sign. It's not a good sign. Okay, and even till today, some people still have some of these things. Even today that we have modern science, some people are still afraid of solar eclipse. Okay, that is why lectures like this are very important to educate the public about these kinds of things. So, but today we know that it is not a demonic curse on Earth, and it is not a mysterious event. It is pure physics, a pure natural event. So it is just the look at that. It's just the moon casting its shadow on Earth because the sun is shining. See that? So this is exactly what is going on. Okay. So and when you know this, it makes a huge difference. So when you know this, do the eclipse, you come outside, you enjoy, you're excited. You don't hide. Some people go hide. It's funny. Some people go hide it. So you just come outside to feel it, to experience it, to take pictures. You are happy. Wow. This is once in a lifetime event. So you don't have to have, to just hide or be afraid or be crying. You don't need all of that, okay? Because modern science have been able to tell what it truly is. And even solar eclipse had even helped us to advance science. For instance, in 1868, eclipse, there was a total solar eclipse in 1868. Okay, so scientists were able to detect to detect helium, the presence of helium in the spectrum of the sun. So before they even discovered it here on Earth, okay, before they even discovered it here on Earth, okay, they have only discovered it in the sun because they did investigation doing solar eclipse. How about confirmation of Einstein's general theory of relativity? The solar eclipse was used to confirm it. And let me explain this idea to you, okay? Einstein came up with the idea of gravity that is different from Newton's idea. Because according to Newton, Gravity is a force that attracts two bodies that have mass. Okay, but Einstein idea is completely different. He said that gravity is not a force; it is just a dent created when a massive object is in space. Okay, because according to this idea, space is a material. Like you have your bed. So imagine your bed. Okay, so if you drop a heavy object on your bed, it creates a dent. Maybe a ball, a heavy ball, it creates a dent. So if you roll, if you drop anything on that surface, around that surface, it's going to roll towards that center, that place, that object created that dent. So that's exactly what is happening here. So that attraction, so that curvature that it creates becomes gravity. So that is exactly what he describes as gravity. So here is the sun creating a dent in the fabric of space-time. So the Earth revolves around that dent created by the sun, and so the moon also. Okay, so even Earth creates its own dent, so the moon orbits around that dent created by Earth. Okay, but what is important? This has a lot of consequences because it means that if you have light sources, like because light travels through space, okay, so as light passes through here, it is going to bend. Okay, that's good. So to test this theory, Einstein uh, took advantage of the solar eclipse because he said that if this is true, if this idea is true, that means it means that the light, the starlight coming from behind the sun would bend. So look at the description here. So you have the sun, okay, then you have these stars at the background, and you have Earth. Okay, during when there's no eclipse, in daytime you cannot. Everywhere is light up, it's lit up. There's no, you can't do that in the daytime because the sun is very bright. You can't look at it. You can't look at this. You can't even see the stars. You can't even barely see the moon. Okay, but during eclipse, the moon blocks total solar eclipse. It blocks the sun, so that I've described that to you. The stars appears and everywhere feels so calm. So these background stars, their paths when they sorry, their path will go like this to your telescope or to your eyes. So, but to you looking at it, it seems as though they are coming from here, but they are coming from behind the star, behind the sun. So that was his idea. So he wanted to use this solar eclipse to test it, and he did. He did use the solar eclipse to test it. And before he did that, did his theoretical calculations. He came up with the angle between the apparent position of the star from its true position is 1.7 arcseconds. And the scientists went around the world, the path of totality, to measure it, and they got this exactly. They got and confirmed that this idea is very true, and that was so amazing. It shook the world, like it literally shook the world. When I was studying this when I was in college, I felt so shocked how smart this man is. Einstein. He's a he's a very smart man. He's a very smart man. It's one of the brightest minds that's ever lived, and I really love him. I love him and Stephen Hawking. Okay, so let me go through the overview of the August 12th solar eclipse, total solar eclipse. Okay, so by next week on Wednesday 12th, there's going to be a total solar eclipse. It's going to start from somewhere in the Greenland, and now this is the shadow this is the shadow I showed you before. It's going to just move, 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 and stop somewhere in the Mediterranean, somewhere there in the Mediterranean. Okay, so if you're in this path, you're going to see total solar eclipse. We call it the path of totality. I'm going to explain what that means. We call it the path of totality. Okay. Then we have other less darker shadows. We call that the penumbra. Okay, let me show you. So we have other lesser darker shadows that are to the right and to the left of this thick dark line here, this totality, path of totality. So each is even wider. It's wider in diameter, in size than this one. So also the people experiencing those ones are people that are outside here. So they will experience a partial solar eclipse. partial solar eclipse. So you can see the map of the globe. This is Canada. It's going to touch some. It's going to cover almost the entire Canada. But I mean, this is like 90, 100%, over 90% of Canada. Then some parts of the United States. It's going to cover the entire Greenland. This is some Europe. This is Sweden. So it's going to cover, in fact, almost the entire Europe, except Ukraine here, or maybe. Then you have Russia. Then it's gonna reach North Africa and West Africa. So, but these other parts are gonna just experience partial solar eclipse. I'm going to explain what that means in details. Okay. So now that we have understood what a solar eclipse is and why it has fascinated humanity for centuries, let us now explore the science behind it. Let us explore the science behind eclipse. So to begin exploring the science behind the eclipse, we have to understand lunar phases, okay? Because as the moon orbits the Earth, different portion of it, you know, shines. We see different portion of it, okay? So for instance, this is a video. I'm going to play this video. Although I wanted, this is a video I saw from the internet, but I had wanted it to start from the new moon, start from here to go around, but started from here. So this is what we see as full moon. So you see all the time, half of the moon is always lit. Okay. So let me make it, let me move it to, let me make it move to the new moon. I can even make it faster. Okay. So it completely blocks. So watch this. So this is new moon. So look, this, you can see yellow here. That's the sun. That's the radiation from the sun. Okay. So here is the moon. Here is Earth. Okay. So during new moon, we don't see the moon. Okay. Call it the new moon. So that's the first stage. Then as the moon moves away, begin to see it. Okay. Begin to see becoming visible. So we have the first quarter. So we have the waxing crescent. We have the first quarter. We have the waxing gibbous. We have the full moon. So full moon is when it comes here. So somewhere here is the first quarter. Somewhere is the waxing crescent. Somewhere is the waxing gibbous. So here is the full moon. Then it continues again, waxing the waning gibbous, and we have the third quarter somewhere here. Somewhere here is the third quarter, and we have the waning crescent. That's the waning crescent, and it comes back again. It comes back again to this place, the new moon. Then repeat. So this thing happens every month. Every month the moon does this. Every month the moon does this. Now, observe something. Is the moon not blocking? Look at the sun. Sun is somewhere there. Okay, we cannot see, but look at the radiation and look at the moon. Look at. Let me position this very well. Okay, sorry. Okay, so look at the moon. I thought, because when I introduced this topic, I said it is the shadow of the moon that is cast on the on Earth that we experience as eclipse. Okay, now in some textbooks they don't even emphasize on the shadow. They will just tell you eclipse happens when the moon crosses between the sun and Earth. But now it is crossing the moon. It is crossing it. But so now let me ask you a question. Do we experience solar eclipse every month? And the answer is no. So if we experience a new moon every month and we don't experience total solar eclipse every month, so what is happening? So what is happening? Okay. So why don't we have a solar eclipse every month? So it actually shows that having the moon between having the moon between the sun and Earth is a necessary condition, but not all the condition, not a sufficient condition. So there are other factors. That's why I was talking about the shadow. Okay, so it's not just necessary having the moon between the two. Okay, so you're going to see why. Okay, so the answer lies in the tilt of the moon's orbit. So when you look at the tilt, you think it is horizontal plane, like you have like like your fan, you know. Just imagine your that this is your fan, this is the center of your fan, this is one of the blades moving around. No, that is how you would normally picture this, but that is not what is going on. This is the moon is actually tilted with respect to the Earth ecliptic. Okay, it is tilted by 5.1 degrees. So it is not just horizontal like this flat. It is not just flat. It is tilted. So as it orbits, it goes up, it goes down. So if you're looking at it from the sideways, you can see that it goes up, goes down. But if you're looking at it from above, you might see it like this. If you're looking at it from above, like this, see that? If you're looking at it from above, you think it is just moving straight, just moving horizontal straight. But if you're looking at it from the sideways, you can see that it is tilted. And now you can see the shadow. You can see the shadow pointing out. That shadow that causes the eclipse is always missing Earth. It's always missing Earth. That is why we don't experience eclipse every time we have new moon. Okay? So it is always missing Earth. Now, at what point does the shadow touch Earth? It happens two times it happens two times in a year. Two times in a year. And something happens. You know, this is Earth. This is Earth orbiting the sun, and you can see the tilt, and also you can look at the moon also revolving around Earth. Okay. Now, as it is revolving around Earth, in its orbital plane, and so this its orbital plane with one time coincide with the orbital plane at which the Earth revolves around the sun. So at that intersection is what we call the nodes. Okay, the node. So here is the moon. This is the orbit. This is the orbital plane of the moon. So this is the ecliptic. Okay, this is you can. This is you can. This is not the sun. Okay, this is Earth. But this line is ecliptic. This is just the path followed by the Earth around the sun. So when it coincides with that of the moon, so that point it coincides is called the node. Okay, so if the moon is at the node, if the moon is at the node, and now you have a new moon, then you're gonna have a total solar eclipse. So have you seen it? And it happens only twice a year. That is why we on average we witness solar eclipse twice two solar eclipses every every year. Okay, so look at that. So it's called the nodes. So that is why I don't experience solar eclipse every month unless the moon is at this node. Okay. So question now, another topic I want to talk about is very important. Okay. Why can the moon completely cover the sun? Look at this picture here. You know, the reason why I raise this question is because if you look at the size of the solar system, if you look at the size of this planet relative to the sun, they are incomparable. Like incomparable. Look at this, or look at this. Look at Jupiter and Saturn and these gas giants and ice giants. Look at how small they are compared to to the sun. And look at these other rocky worlds here. We have this is Mars. I hope you can see that. This is Earth, our Earth, and this is Venus, and this is Mercury. Okay, okay. I hope you can see Mercury there. It is very tiny. Mercury is almost like approximately the size of the moon. I think it's slightly higher. Okay, but let's assume. Just look at how tiny, as a grain of sand. Look at how tiny it is. Okay, so I imagine it is orbiting like something that small is orbiting Earth. That is the Earth, the moon. So you see, you can't compare Earth to the sun size. Okay, you can't even compare the two. You can't even do that. It's incomparable. But why is it that during the eclipse it covers the moon covers what is as small as a grain of sand covers the entire sun. So why is that? That is why I this topic I said why can the moon complete cover the sun? Why can it completely cover the sun? So now, to answer that question, we need to look into the data. If you look at the diameter of the sun, that is 1,1,392,700 kilometers, and that of the moon, which is about 3,474 kilometers. If you use the diameter, if you divide the diameter of the sun with the diameter of the moon, you discover that it is just 400 kilometers, or just 400 times, sorry, not kilometers, 400 times larger, okay? 400 times larger. And if you do that to the average distance, they are from Earth. For instance, the distance of the sun from Earth is about 150 million kilometers, and that of the moon from the sun is about 384,400 kilometers. If you do the division, it's also get 400. Okay, so that is why. So it's because of how far away. That is how. Because I'm going to use this to explain it. Let me use this to explain it. Let me use it. So imagine this. Imagine this. This is a real car, and this is a toy car, the one you buy for your kids. Just a toy. You can even hold it to your hand, finger like this. So when you bring them very close, it is incomparable inside. But imagine you walk further out. You keep walking backwards, so it can, to a point they remain the same size. So that's exactly what is happening. It's because the sun is very massive, but it is far away. It is very far away. That is why during eclipse it appears as if it could cover, it could cover the sun. So I hope you can understand why that is. So let us go into the types of solar eclipses. I'm going to be talking about the moon shadow in terms of that types of solar eclipses. So, during solar eclipses, the moon casts its shadow. I've talked about that before on Earth, and produces three distinct shadow regions. So before I go into those three or four shadow regions, so here is the picture taken from the International Space Station during one of the one one total solar eclipse there. This is the International Space Station. So you can see this dark spot. This is the shadow of the moon. So look at this other region, there's no shadow. So if you are here, you may not even witness an eclipse. Okay, but if you're here or surrounding it, you can witness an eclipse. Okay, so just that is by the way. So umbra, the umbra is the darkest central portion of the moon's shadow. So I have crafted this analogy. So imagine this is Earth, though Earth is generally blue in color, and you have so this dark spot is the shadow, just the shadow there is the shadow. Okay, so this is the darkest region of that shadow is called the umbra. Okay, and if you are, so I just use that yellow star as a human being. So these are human beings that are looking at observing the solar eclipse. So if you are part of these people that are observing this, so here are the characteristics of the things you're going to see. The sun is completely heated. So if you're in that dark spot, you see that the sun is completely heated. So observers experience a total solar eclipse. The sky becomes very dark. So then you're going to have the corona becomes visible. So that I told you the corona is like the atmosphere of the sun. You cannot see that during the daytime or other days. You can only see that during eclipses. You see that, you see these shapes, atmosphere of the sun. You can study it if you're studying the sun. Okay, so then the path. So that path, that shadow moves is called a path of totality, because it's not standing still, because the moon is moving relative to the earth, so it moves, shadow moves, so it moves. So that path it traces becomes the path of totality. I hope you know what I'm talking about now about that. So, but it is not just only this. I've told you there are other ones, other shadows. So now bring us to penumbra. Penumbra. So here is the set diagram, but this time I've indicated the penumbra. So here is the umbra. So penumbra surrounds the umbra and is bigger. It is wider. Okay, it covers even wider regions. And if if you are in this penumbra region, you're going to see a partial solar eclipse. Okay, so depending on the, so if you are closer here, the partial would be like almost like a total. If you are here, the partial would just look like it's just ended. Okay, so look at that. So these are, so if you are the outer or the outermost part of the penumbra, you're gonna see, can experience this kind of eclipses here. But if you are closer to the penumbra, okay, to the umbra, you're going to see some things like this. But if you are in the umbra, you're going to see this kind. So I just want to explain that to you. So that brings me back to this. So these other countries here, we experience penumbra, penumbra. The UK, we experience penumbra, penumbra. I think UK is very close to the, but it's just still penumbra. So you have the Canada, but this country experience umbra, the total solar eclipse. So here's the ray diagram of the total and partial solar eclipse. So here you have two rays from this point. So you can even draw this and sketch this. So you draw one. This one will touch the surface of the moon, and you continue drawing it until it touches there. Then you draw another one here. It scratches the surface and it touches there. So they are going to form the penumbra. Then if you draw another ray diagram, so this one will start from here, touches a continue coming here. It's going to form the umbra. So the same thing comes here. So form the umbra. So you have the penumbra, you have the umbra. So that is the red diagram. Just want to show you that for reference sake. So we have the orthonumbra. Orthonumbra is very tricky. So look at this type. Look at this type. Look at that. You know, you see some kind of a ring of fire. Okay. This is not the way total solar. This is another. It's almost like another kind. Okay. Okay. So it is because of this. Let me show you from the red diagram so that you can see what is going on. So it is because during this time, the moon is in what we call the apogee. It is farther. It is in its farthest point from Earth. It's called the apogee. Okay. So when it happens, this shadow that could have formed the umbra converges in space. So look at that. It converges here and crosses. So the cross shadow, now that cross shadow is called the antenumbra. Antenumbra reaches Earth. And that is what causes that ring to form. Okay? Because this point, usually forms the umbra. It didn't reach Earth. It just converges somewhere in space. Then it crossed, it crisscrossed, and then it's the crossed shadow, the crossed umbra or antenumbra now reaches the Earth's surface. We also call this annular eclipse, and it gives rise to this. We call this the ring of fire. We call this the ring of fire. So this is what I was talking about, the apogee, the perigee. This for total solar eclipse, that the one is going to happen on 12th of August. The moon is going to be at the perigee, closest to Earth, so it will completely block it. It will completely block it. But apogee, it is rare. It's rare. It's rare, so it happens here. It's rare, okay? So we have another one. It is not another type, but just like a combination of annular and total. So this happens because of the curvature of Earth. So imagine an eclipse shadow starts off from here because of the curvature and how far away, how Earth is curved. So it's going to form an optonumbra, like I explained before. But as the shadow moves, because of the curvature of the Earth, that point that converged in space when it was here will now be able to touch the surface of the Earth and becomes total eclipse. But as shadow moves again, it continues and forms an optonumber. So we call it the hybrid. It is very rare. It is very, very, very rare. Okay. So have you ever wondered that when you were growing up, you probably witnessed eclipse. Okay, for instance, when I was in, I think it was our primary school or secondary school, I witnessed total solar eclipse. So our teachers brought us outside. Okay, so but now I've not been able to witness it again. So why? So why is it that? Why is it always? Why is it called an event of a lifetime? Okay, why is it called an event of a lifetime? If like that's happened in your region, it is likely not going to happen again in your lifetime. So why is it so? Okay, it's because normally eclipses happen every 18 months. Okay, but once it happens in a particular region, it's not going to happen again until after like 300 or 400 years. So if you're going to live as long as that 300 or 400 years, you are going to witness another eclipse. So look at this path. Look at this path. So as eclipse happens in this path, it's not going to happen in this path again until after between 300 to 400 years. So that is why you don't notice it because of it's because of celestial dynamics. Okay, so celestial dynamics. So let me, if you are planning to observe it, I want to give you some little advice on what to what to look out for and what not to do. So if you want to observe it, you have to buy these solar eclipse glasses or viewers. This kind we call it ISO 123122. You can look for it. You can just Google it. Go buy it from Amazon. Okay, so you don't have to look at the sun directly. Don't do that. It is not advisable. It will burn your eyes. Okay, then also you can construct a homemade solar filters. You can use it to cover your telescope. So you don't point your telescope to the sun and want to view it. You're going to get. In fact, you even made it worse. Okay, you made it worse than just looking directly to the sun. Okay, so if you put it, put the filters, it's going to reduce the solar glare to this, so you can look at it like this in the telescope with filters on. Okay, so you need to use. You can construct a pinhole projection. You were taught this in physics, right? So you can go back to your physics textbook to consult how the principle works. You can construct that. You can even construct this one. It works with the same principle. Okay, so never you point your eyes or telescopes or your binoculars directly to the sun because you're about to damage your eyes. So thank you so much for your attention to these lectures, and you can post your questions and your comment to the comment sections. Thank you very much.